Okay, so we're going to look at section 3.3, okay, which is on the factor theorem and long division. What's nice about long division is it works on any problem. There is a shortcut to long division called synthetic, but synthetic division only works on certain problems. So we're going to first learn how to do the division that will work everywhere, and then tomorrow we'll learn the shortcut that will work some of the time. All right, so just a couple of reminders about what zeros or what roots are. Remember that zeros or roots are numbers that you can plug into a formula and the answer comes out to 0. So it's a value you plug in for x. And when you do that, you get 0 for y. So this next statement is called an if and only if statement. That's what IFF stands for, if and only if. And that's a logical word, meaning you can read the sentence forwards or backwards. If you wanted to put it in another kind of context, you can read it the original way or its converse, and they are both true. So this says that if a certain number is a root, then when you plug it into the formula, you get 0. Or if you have a number that you can plug into a formula and get 0, then it is a root. So you can read it. You can read that sentence both ways. Technical name for that is the original way, and then the converse is when you switch the beginning and the, like the if and the then. So we're going to look at how we can use long division to find roots of polynomials. And really what long division allows us to do is factor, which allows us to find roots. So long division is really helpful for factoring. So let's look at an example with numbers. Okay. Let's say that I wanted you to factor the number 12. Okay. To factor it means to write it as a product. So let's write 12 as something times something. Now, I'm going to give you a hint, and I'm going to tell you that 3 is a factor. If you know that 3 is a factor, how would you get the other factor? Yeah?
You would then divide the 12 by 3, getting the number which is going to be 4.
Yeah. So if you have a number that is a factor, and you want to use that number to find another number that's a factor, you do division. So in this case, if I tell you 3 is a factor, you know that 3 times something is going to give you 12. To solve for something, divide each side by 3, and you get 4. And of course, you can plug it back in and check it. 3 times 4 gives you 12. That's one that's, obviously you wouldn't really have to go through those steps, but we're going to do something like maybe I'll give you a polynomial, like x cubed plus 2x plus 9, and I'll say x plus 7 is a factor. Tell me the other one. Well, if you know that x plus 7 is a factor, you can do division to get the one you don't know. We have to go through how to do it. It's a little more complicated than just dividing 12 by 3, but it's the same idea. Now, notice right here. I want you to think in terms of like quotient and remainder. When you divided 12 by 3, what did you get for a remainder? Yeah?
0.
0. You didn't get any remainder. In fact, if you divide 12 by any number that's a factor of 12, you will always get a remainder of 0. And that's an important idea. So the quick way to figure out if something is a factor is to figure out what's the remainder when you divide it in. If you divide something in and get a remainder of 0, it's a factor. If you divide by something and get a remainder that's not 0, then what you divided by is not a factor. Right? Take 12 and divide by 7. You're going to get a remainder. That's because 7 is not a factor of 12. Any questions on that idea? I basically just said that too. So if you divide two things and you get a remainder of 0, then you know what you divided by is a factor of the numerator. Exactly what you just said. So factoring a polynomial makes it very easy to find roots. Okay? Just think about how you solve a quadratic. The first approach you usually take is you try to factor it. You can use quadratic formula, but there's more to remember with it, and there's more that can go wrong because there's more steps involved. But if you're good at factoring and the numbers work out, factoring is always going to be faster than quadratic formula. I would say most of the time. So maybe not always, but most of the time. So that process that I just showed you with the number 12. I want you to factor 12. 3 is a factor. Find the other one. We can do the same thing with a polynomial. And what I'm going to show you now is the steps for dividing one polynomial into another. Okay, there's going to be 5 steps. What I'm going to do is I'm going to put a problem on the board, and I'll show you a step, and then we'll do that step in the problem. So if you want to do this like side by side, the steps on one side, put the example on the other, or just leave like enough room to write 5 steps, a couple inches on your paper, and you can put the example below. So the first step is basically just setting it up. So when you are doing long division or synthetic, you have to make sure that the dividend, which is the part underneath the symbol, has every single term from the highest exponent to the lowest represented. So we've got a cube term, we've got a first power term, and we've got a constant. Are we missing any term? Yeah. We're missing the x squared term. So what we're going to do is we're going to fill in as 0x squared. The reason we need to do that is because we're going to have to line things up in like terms. So we need a column for the cubes, squareds, linear, and constant. Okay, so let's make a column for squared. And remember, generally the way long division works is all your work is going to go down and to the right. So you don't want to start a long division problem right on the right edge of the page, because you're going to have to go down and to the right. Okay, so let's put in x cubed. We don't have any x squareds. Okay, that's just a placeholder. We have a negative 8x and a plus 3. Okay, so there's your first step. Okay, second step. We're going to divide the first term of the divisor, which in this case is x, into the first term of the dividend, x cubed. What do you get if you divide x into x cubed? Yep.
X squared.
X squared. Perfect. Where you put the x squared doesn't really matter. Just put it back above the horizontal line. It doesn't have to be lined up with anything special. Now, you're going to multiply your answer that you just got in step 2, x squared, times each term in the divisor. So it's like a distributive property. And this is where we have to make sure we put the result in the correct column. Okay, line up like terms. Jack, if I multiply that back out, what's x squared times x.
It'd be x to the third,
What is it?
right? X to the third.
Yeah, x to the third. So x to the third. And Jacob, if I multiply x squared times negative 3, actually, let me move that over here. X to the third. Sorry. What's x squared times negative 3?
X squared times negative 3 would be negative 3x squared.
Yep. That's the next step. Okay, now we're going to subtract. And that's subtracting columns that we just did in step 3. Okay, so the way I do that is I put a minus sign and I go like that. All right, let's subtract it. Michael, what do I get if I do x cubed minus x cubed? 0. Okay, that's gone. Something should always cancel out in this step. Sometimes 2 things. That's nice, but this time it's only 1 thing. Mia, what's 0x squared minus 3x squared? Plus 3x squared, yep. Okay, so we got that. And that's step 4. And now the last step, bring down the next term and repeat it. So my next term is negative 8x. Now, you keep doing this until either you get a remainder of 0, then you're done, or until this exponent is smaller than that exponent. We had a 1 as the original exponent on the outside for the divisor. Now we have a 2 inside. It's not smaller, so we got to keep going. Okay, so now divide x into 3x squared. Max, what do you get if you divide x into 3x squared? 3x. So we get plus 3x. Now you're going to multiply the answer back out to each term. Sophia, what's 3x times x? 3x squared. And Lily, what's 3x times negative 3? Negative 9x. And Jacob, what do I do with those columns? Yeah.
Oh, you subtract?
Yep, I'm going to subtract them. And Cole, what's 3x squared minus 3x squared? 0, that's gone. Rory, what about negative 8x minus negative 9x?
Negative 17x.
Well, if it was negative 8x plus negative 9x, that'd be negative 17x.
Oh, okay. Negative 1x.
So negative 8x plus 9x. Just 1x, right? Because that minus a minus becomes a plus. Bring down the next term. The degree on the x now is a 1. The degree on the x on the outside is a 1. We need to keep going till the degree on the inside is smaller. So this is the last step. Yep. Negative 9x. Positive 3x times negative 3. Okay. Now, let's divide x into x. Jade, what's x divided into x? So you're basically off to the side, you're doing x divided by x. 1. Okay, now we're going to distribute that back out. So distribute out the 1. How about Ryan? What do you get when you distribute 1 to the x? So we're going to distribute that 1 back out. Sorry, did you tell me? No. No. So distribute the 1 back out to the x.
All right.
So 1 times x is x. So x. Now we have to distribute the 1 to the negative 3 is x. What's that going to be? Negative 3. All right. And Zach, what do I do with the... How about Joe? What do I do with the columns there?
You subtract.
Yep, I'm going to subtract them. Okay, so subtract those, and then once we do that, that's going to be our last step. We're going to be done. So James, what do I get when I subtract these columns?
Well, x comes out to nothing,
Mhm.
and you get 6.
6, and that 6 is my what? That's my remainder. So there's 2 ways we can write this answer. One way, you can do it down there if you want. I just have more space here. So the quotient and the remainder. The quotient is x squared plus 3x plus 1. Remainder, 6. The other way you can write it is the same way you could do it if this was numbers. Let's say you had 13 and you divided it by 5. What's the quotient when you divide 13 by 5? Yep.
2.
2. And what's the remainder?
3.
3. So another way you can write your answer is quotient plus remainder over the original denominator. So you could write 2 plus 3 over 5. Or you could put that as a mixed number and say 2 3/5. Okay? We can do exactly the same thing with a polynomial.
Or you would just say 13 over 5.
Right, but we're going to have to actually write it out as a quotient and a remainder. So you're going to have to find it and either write it like this or write it as quotient plus remainder, which in this case was 6, over the original denominator, which was x minus 3.
Where did you get 2 from?
That's how many times 5 goes into 13.
Oh.
2. So either way, okay, I just showed you this so you can see it with numbers, quotient plus remainder over denominator. The nice thing about the second way is you could type this in y1. You could type the original problem in y2, and then if they look the same, then you know you probably did it right. When you write it quotient and remainder separate, there's really no quick way on the graphing calculator to check your answer. Okay, any question on writing it either way? Okay, that's a problem you could do synthetic division with if you knew how to do it. And that's a problem you cannot. So this time we've already filled in zeros for the terms we were missing. Most likely you would have to do that step on your own. All right. So who can tell me what's the first thing that we're going to divide on the outside into something on the inside? What on the outside into what on the inside? Yep.
The biggest thing inside is going to be 2x to the 4th. That means you need to have x to the 4th, meaning you need to multiply it by x squared, the entire equation.
So what are you dividing again? What by what?
You're dividing 2x to the 4th by x squared. Well, by 2x squared plus x plus 1, but the first thing you're going to like get from that would be x squared.
Yeah. So you're going to divide 2x to the fourth by 2x, and then you do get x squared. So that's your first step. All right, and now, Gabriella, what do I do with that x squared?
You multiply it by everything.
Yep. So we're going to multiply that back out to everything. So let's do that. Anna, what's x squared times 2x squared?
It would be 2x to the fourth.
2x to the fourth. Corwin, what's x squared times x?
X squared times x would be x cubed.
X cubed. And the last step, Lily, what's x squared times 1?
X squared.
X squared. Okay, and Richard, what do we do with those columns?
She subtracts like last time.
Sorry, say it again.
She subtracts it.
Subtract. Yeah. So we're going to subtract all of them. Michael, what's 2x to the fourth minus 2x to the fourth?
0.
0. That's gone. Mia, what's negative x cubed minus x cubed?
Right. Negative x. 2x to the third.
Yeah, negative 2x to the third. Okay, and Veronica, 0x squared?
2x to the squared.
Oh, cubed, thank you, yeah. Cubed. What's 0x squared minus x squared?
Negative x squared.
Negative x squared, and bring down your next term. Just a 0, just there as a placeholder. That's all it really is. Okay, Aiden, what's the next thing on the outside that I'm going to divide onto the inside?
You do negative x. When you multiply 2x squared plus x plus 1 times negative x.
Okay, how did you get that? In case somebody's not sure, negative x.
Or you need to just, because negative 2x to the third is by negative 2x to the third.
And what did you divide that by?
Negative 2x to the third
Yep.
minus x plus minus 1.
So what would go in the bottom right here to figure out what goes here? Yep. 2x to the second. So you divide the term on the, where'd that 2 come from? Why is that there? Negative x cubed. And we're dividing by 2x squared. So then when you do that, you said you got, what did you get?
Negative 2x to the third.
You got a negative 2x to the third.
Negative x.
What's that? Well, I'm just going because some people might, they might not know exactly all the steps. I know for me, like I can just go through it real quick, but yeah. So up here is going to be negative x. Now we have to distribute that back out to everything. Xavier, what do you get when you distribute the negative x back out?
You're going to get negative 2x squared minus x minus
Cubed.
4. Oh, yeah, negative 2x cubed minus x squared minus x.
Minus x. And then subtract the columns.
Yep. And then you're going to be left with positive x minus 2. You're going to be left with positive x just from that, but then you're going to end up with the remainder of x minus 2 because you need to break the last negative 2 down from the divisor thing.
Okay, something important there I think we should explain before we just write x minus 2. What else happened there? 'Cause I bet
Everything
this-
cancels out.
Right, the x squared's also canceled out. Okay, that doesn't always happen, but this time 2 things canceled at the same time. When that happens, well, we're done. Because now the degree on the inside is a 1, degree on the outside is a 2. Since 1 is smaller than 2, you can't go anymore. All right. So what's my quotient?
X.
Like
X squared minus X.
x squared minus x. And my remainder? Yep.
X minus 2.
X minus 2. Or you could write it as x squared minus x plus x minus 2 divided by 2x squared plus x plus 1. That's quotient plus remainder over denominator. Any question on that one? So what does that mean then? Because we got a remainder of x minus 2, what does that mean about this? Yeah?
So it means that you can't like fully, in fact, you can't fully divide it out to get like just a full number. And so the remainder is going to be the x minus 2 over 2x squared plus x plus 1.
Okay, so I agree, there is a remainder, but what does it mean in general when there's a remainder when you do division? Yeah?
It's not a factor.
It's not a factor. Whatever you tried to divide doesn't go into whatever you did evenly, and it's not a factor. How about here? If you were trying to factor x cubed minus 8x plus 3, is x minus 3 a factor?
No.
No, because we got a remainder of 6. So far we did long division and we did not get any remainders of 0. All right, so this equation you can basically write down for any problem we do. I'll take the one that we did first and write it down. But it's a way to check your answer. Let's say you did it with numbers. Okay, actually numbers will be even easier. Let's say you had 13 and 5. If you divide 13 by 5, we already did this. What was the quotient? 2. And what was the remainder? 3. So let's see if this little formula works. It's a way to check your answer. 13, if you did that correctly, should equal what you divided by times the quotient plus what you got for a remainder, 3. Does that work? Yeah. So it's just a way you can check your answer. If you take what you divided by and you multiply by the quotient and you add your remainder, that should give you the numerator. If it doesn't, then something's wrong. I won't actually do it out with a polynomial to check it because that would take a lot longer. But with numbers, it's really quick to check. Yeah.
Could you read out that sentence? Because I'm having difficulty understanding. It says, if f of x and h of x are polynomials, then their exit is polynomials of what? Of polynomials.
Q and x, which would be a quotient, and r of x, which would be your remainder. So anytime you divide two polynomials, you're going to get some quotient and some remainder, always. In my case, I did 13 divided by 5, and the quotient was 2. And remainder was 3.
You'll never happen to divide by quotient or divide and then get no remainder.
You could, yeah, you could. Like, so let's say you had, instead of these numbers, let's say you did 14 and 7. It would still work. So if you take 14 and you divide by 7, the quotient in this case would be 2, and the remainder is 0. So now let's check and see if it works. 14 should equal 7 times my quotient plus my remainder. Yeah. So this formula works all the time, no matter if you do it correctly, no matter what quotient and what remainder you get. Yep. So remember that when you divide, this is how you know when to stop. The degree of the remainder is less than the degree of the divisor. So the exponent on the inside is smaller than what's on the outside. Or you end up with a remainder of 0, and then you're done. So what I'm going to be getting at here is I'm going to show you a quick way to find the remainder in a problem. This shortcut, it's only going to work if you divide by something relatively simple. If you were doing this last problem, I don't have a quick way for you to get the remainder here. But I do have a very quick way for you to get the remainder here. Yep, I'm going to go back. So think about if you divide by something linear. Okay? I don't care what's in the top. You have something in the top, and you divide by something linear. Linear means it's x minus a number, x plus a number. The denominator is relatively simple. It's linear. We just said that the degree of the remainder is always less than the degree of the divisor. Here's your divisor. What's the degree of a linear divisor? Yeah?
1.
That's a degree of 1. The degree of the remainder is less than that. What's less than degree 1?
0.
Degree 0. What does degree 0 mean?
1. That the entire number is going to equal 1. Any number to the 0th power is 1.
Okay, it doesn't mean that you always have a 1. Just like if I had a linear polynomial, it doesn't mean it's always x minus 5. It could be x minus 7, x minus 12. There are other linear polynomials. What is a constant polynomial in general?
X to like 1, x to the 1, x to the 2, x to the 3.
That would be linear, quadratic, and cubic. I'm looking for below that. Degrees.
X to the negative?
Well, to the 0 power. The x is to the 0 power. But you also have a, what else?
Remainder?
Yep, you're going to have a remainder. And what do you call a degree 0 polynomial? Like degree 3 is cubic, degree 2 is quadratic, degree 1 is linear, degree 0 is, what is it? Constant. Right. When you divide by something linear, the remainder is a constant. It doesn't have to be 1. It could be 2, 3, 5, 10. But it's just a number. So when you divide by something linear, you're guaranteed to get a remainder that's a number. No letters in it. Well, right there, that makes the remainder easier to find because there's no letters. So let's take that formula that we just had. Where was it? Right here. F of x equals h of x times q of x plus r of x. And let's apply it specifically to the case where you divide by x minus a number. So now instead of this just being anything random, it's going to be x minus a number. Okay. So it would look something like that. F of x can be any polynomial you want in the top, but you have to divide by something linear. This is the trick I'm going to show you. If you're going to divide by something more complicated than linear, then forget what I'm about to show you. It's not going to work. Okay, so that means, let's go back up. The numerator equals what you divided by times the quotient plus the remainder. So the numerator is going to equal what you divided by, x minus c, times the quotient, we don't know what that would be, plus the remainder. So it's exactly the same formula you had up above. I'm just focusing now when the denominator is something that's x minus a number. And remember, the remainder is a constant because it's degree 0. Now, I want to look at what happens if we plug in a certain value for x. Okay, and not just a random value. I specifically want to plug in the number after the minus sign. And watch what happens. We're going to plug in the number after the minus sign in that formula. Let's see what happens. So again, take the number that comes after the minus sign and plug it in for x. Well, when you do that, that means all your x's are going to change to c's. Whatever this is, maybe it's a 2, maybe it's a 5, we don't know what it is, but it would be a number. Okay? We're going to call that c for now. So what would f of c equal? What would come right after the equal sign if you plug in c? You don't have to simplify it, just literally change the x's to c's. Yeah?
It would just be equal to the r because it would change.
Yeah, tell me about this.
It would make that little bit of it equal to 0, which is undefined, so you couldn't do that to begin with.
Well, it would be 0. It wouldn't be undefined. It would be 0. So that is defined. So it's the value 0. And then what would be next to it?
Well, the other thing is the q of 0.
Q of, what are we changing
C.
x to? C.
But that part of it wouldn't really matter
Right.
much because multiplication
And what else would you have?
add 0. R
Plus r.
not 0.
So now, this part, c minus c is 0. And 0 times anything basically cancels that whole part out. So you end up with that. F of c equals r. And what's r? Yep,
The remainder.
it's your remainder. So that's a formula to find your remainder. If you take the value after the minus sign and plug it into the f formula, which is what's in the top, you will end up with the remainder. Let me show you how that works on the first one.
For c minus c times q times c, we're assuming that c is x to 0, or just, we're assuming that there's going to be a 0 in there, meaning that if you multiply all together, it's going to be 0. That's why it all cancels out.
Cancels out because that's 0. Yep.
C minus, okay,
Because c minus c is 0.
got it.
Let's look at this one. We divided this by x minus 3. What's the number after the minus sign in the divisor? Just the number after the minus sign. 3. Let's take 3 and plug it into what would be the numerator if you wrote this as a fraction. Okay, x cubed minus 8x plus 3. So take the 3 and plug it into x. 3 cubed minus 8 times 3 plus 3. What's 3 cubed? 27. 8 times 3? 24. And what's 27 minus 24? Lily? 3. And what's 3 plus 3? 6. And for the remainder on this problem, we got 6. So by taking the number that comes after the minus sign and filling it in for x in the dividend, or the numerator if you want to call it that, same thing, you will get the remainder. But the trick is it only works if it's x minus, and then you plug in that number. If you want to find the remainder here, I don't have a faster way to do it. This is not x minus a number. It's too complicated. So this theorem is called the remainder theorem. If you have any polynomial you want, and you divide by something that's x minus a number, the remainder is found by taking the number after the minus sign and plugging it into the numerator, which I'm calling f of x. So now I could give you a problem that has like something like this. You should be able to get the remainder there in under 15 seconds with a calculator. Now, if you're trying to do that with long division, remember, you have to represent every power from the highest to the lowest. So you need the 3x to the 45th, 0x to the 44th, 0x to the 43rd, 0x to the 42nd, all the way down. And if you try to do long division with that, it's going to be awful. You're going to have almost 50 terms in your dividend. If all I want is the remainder here, all you have to do is take the number 2 and plug it in for x. It's a big number, but you just 2 to the 45th power times 3 plus 32 plus 6. And then that would be your remainder. All right, so you definitely don't want to try to find the remainder by doing long division in a problem like that. If they wanted the quotient, well, then you'd have to do the long division, but I wouldn't ask you to find a quotient with something like that. It's too many terms. Okay, so both of these problems, we're going to find the remainder. Two separate problems. I am going to reuse the numerator. So this will be the numerator in both. And then one time I'm going to divide by x minus 3. And the other time I'm going to divide by x plus 1. And if you're already thinking, well, you said it had to be x minus a number. Well, that could be x minus a number. And we'll talk about that when we get to it. Okay, so the first one is f of x divided by h of x. Okay, step one, look at h of x and ask yourself, is h of x x minus a number? Okay.
H of x is x minus a number.
Yeah, h of x is x minus a number. So the trick is you take the number after the minus sign, not the minus sign with it. Jack, what's the number after the minus sign here?
2x.
No, for our divisor.
Oh. Is it the 3?
The 3. So we're going to take the 3. And where are we going to plug that 3 in to get the remainder? Yep. In which function? In f of x. Take the 3, fill it into f, and that will give you the remainder when you do this. So we're going to have 3 cubed minus 2 times 3 squared plus 3 minus 5. So we get 27 minus 18 plus 3 minus 5. 27 minus 18, that's going to give me how much? Nine. And let's just finish that all up. What's 9 plus 3 minus 5? Yep.
It's going to be 7.
7. That's your remainder. So what does that mean about h of x compared to f of x? Yeah? It's not a factor. If you were trying to factor f of x, x minus 3 is not what you should use. All right, let's try. Yeah.
Is that like a type of problem because like you have a polynomial us like that x minus 3, and then we have to find the remaining.
Yeah.
Okay.
Yep. Or I might tell you I might actually give you one that works and say, all right, x minus 2 is a factor. Tell me the other factor. And I don't think most people know how to factor a cubic, but if I told you one of the factors, you could divide to get the other one, just like we did with 12 and 3. Yep.
So that didn't know if we'd have to find the factor.
Well, in this case, you can't because the remainder wasn't 0.
Yeah.
So, no, I have to start you off with one that actually works. Okay, so now we're going to divide by g of x. Is g of x minus a number, the way it's written? Yeah.
On this model, we can change it to x minus -1.
Right, you can make it x minus -1. Now it is x minus a number. What's the number that comes after the minus sign? -1. And where are you going to fill that -1 in?
You're gonna fill that into the f of x equation.
Yep. So now plug -1 in for x.
-1 to the third minus 2 times -1 to the second plus -1 minus 5.
Yep. Plus, you could put plus -1, or if you just want to do -1.
Yeah. -1 plus 5.
And then plus 5. Is it a plus 5 or minus 5 at the end?
Minus
5.
Minus 5.
So -1 cubed will give you -1. -1 squared is 1 times -2. -1 minus 2. And let's just finish that up. What's -1? -3 minus 1 minus 5.
9, -9.
-9. So what does that mean about g of x?
That it does not factor completely. That's not a multiple of it. That is like have a remainder, so it doesn't like fully factor in.
Right. G of x is not a factor of f of x. What is a factor? Well, we don't just want to keep guessing all day and trying things. There's a better way to figure out what actually is a factor, but that's not really what we're doing today.
That would be completing the square thing, right? To find what the factor of it is.
Well, it's a cubic, so you can't complete the square with a cubic.
Complete the cube.
How do you do that?
I thought that was like you said there was like a long equation for like complete the cube, where it's like it's not just these, but it's a whole bunch of things.
Yeah, there is a formula. There is a formula for finding roots of a cubic, which I guess you could use it to factor. It's not really completing a cube. I don't know if that's a thing or not. I'd have to look that up. I've never even tried, but it could be. Who knows? Okay, so now let's look at this. The factor theorem. The factor theorem is basically just the remainder theorem, stating that if you get 0 as a remainder, then what you divided by is a factor. So that's what it says. If f of x is some polynomial, and you divide by x minus c, and the remainder is 0, then what you divided by is a factor. And you can say it both ways. If something is a factor and you divide, you'll get remainder 0. Or, if you get remainder 0, then what you divided by is a factor. So you can say it the original statement and its converse. So now, let's actually do one that's a little more satisfying. Let's use the factor theorem, which is just the remainder theorem getting 0, to show that x plus 2 is a factor. So to show that something is a factor, what you're really going to do is divide and hope that you get a remainder of 0. If you don't, well, something's wrong because they're telling you to use the factor theorem to show x plus 2 is a factor. They're not saying use the factor theorem to determine if it's a factor. It is a factor, but we're going to check it. Okay. So we need to be dividing by something of the form x minus a number. Is our divisor x minus a number? No, could it? Yeah?
X minus -.
We could make it x minus -2. Now, what's the number, Sophia, after the minus sign there? What's the number after the minus sign there?
Oh, it's good.
So you want to look at writing it as x minus, and what would be in that box? -2. Yep. So now fill -2 into the numerator and see what you get. What's -2 cubed? That'd be -2 to the 4th. -8. What's -2 squared times 5? Yep.
20.
20. 5 times -2, -10 minus 2. What's -8 plus 20?
12.
And what's 12 minus 10 minus 2? 0. So we just got a remainder of 0, which means what?
X plus 2 is factor.
Yes. So now we could write this. X cubed plus 5x squared plus 5x minus 2 equals, well, we know one of the factors is x plus 2. How would you get the question mark and figure out what the other factor is?
Divide the other side.
By
The x plus 2.
x plus 2. And divide the other side by x plus 2, and you could solve for the question mark. This is like me saying 12, 3 is a factor. How do you get the other one? Divide by 3, and you get 4. So there is no quick way to do that. Unless you know synthetic division, that would be a pretty quick way.
There's a quick way of representing it. Just do the x cubed plus 5x squared and all that over the x plus 2.
Yeah, that's what you'd have to do, and if they did want that other factor, they'd want you to do that. But in this case, you don't have to. It was just prove that that is a factor. Okay, so we're going to just mention a few different things about roots and zeros.
Okay, so sorry, I'm like backtracking a little bit. When they said when we actually do a problem like that before, do we have to find the other one, or do we just?
No, the directions there didn't say to factor. It just said use the factor theorem to show that this is a factor. So in this problem, no.
Okay.
In other problems, yes, you might have to do out the long division or synthetic if you already know it. If you don't know synthetic, we're going to do it tomorrow. So remember, what does a root mean? Okay, it means it's a number that you could plug in for x and get 0 for y. Let's put an example up so we can kind of work with it. Does anybody see a number you can plug in for x there and get 0? Yeah?
One of the ones that we can do is x plus 1, and I also know the other one that we can do for this.
So what number would you plug in for x and it would come out to 0?
Yeah. Well, it would be -1, and the other one is -2.
Perfect.
Those are the two ones.
You can check, but if you plug in -1, you get 1 minus 3 plus 2. And if you do 1 minus 3 plus 2, you get 0. So let's just work with that number for now. -1 is like our c. So -1, it's not the only solution, but it is a solution to that equation. We also, instead of calling that number a solution, we can be a little bit more specific, and we can call that number a 0. We can also call that number a root. Now, Jacob, you said, not Jacob, you said that -1 was a root, right? So what would be the other root?
the other one,
Yeah,
it's -2.
it would be -2. So -1 and -2, Jacob just gave us the two roots. Now, he also started to kind of tell us how this factors. I want you to see the connection between the roots and how it factors. How does that factor? Yeah?
X plus 1 and X plus 2.
Yeah, x plus 1 and x plus 2. Now, I normally wouldn't do this. That's perfect. But I want you to see something. X minus -1. X minus -2. So the connection between the roots and the factoring is that if you know something is a root, then x minus that number is the factor. That's the connection. If c is a root, then x minus that number is a factor. And you'll see why that's going to be important in a second, because I'm going to give you roots, and I'm going to have you work backwards to give me the factors. What else happens graphically? A root is where the graph does what? Yep.
It's where it makes a parabola. Is that one?
This one might be a
I
parabola.
thought you said like square root. So if something is a root of it, then I think it'd be along the x-intercept.
Yep. So if you have a root, then you know it's the x-intercept of the graph. So calling it a root, calling it a 0, calling it an x-intercept, writing x minus that number, and calling it a factor, they're really all the same thing. They're all equivalent statements. This one is the important one, and that's what we're going to take a look at now. So what I'm going to do is I'm going to give you 3 numbers that are going to be x-intercepts. Okay? I'm going to give you 3 numbers that are roots or zeros. And I want to work backwards to figure out what would be the polynomial that you could type in on the calculator, and it would cross the x-axis at these points. Well, how many roots did I give you in this problem? 3. So how many factors would there have to be?
3.
Would have to be 3. Each one of those numbers would have come from a different factor. And remember, they are roots. So that means you have to be able to take that number, fill it in, and get 0 as the answer. What could you put in parentheses here so that when you fill -2 in, you get 0?
X plus 1.
X plus 2.
X plus 2.
Yeah, 2.
Yeah, I know what you meant. Yeah, x plus 2.
And
What could you put as a factor here so that when you fill in 1, it gives you 0? Yeah?
X minus 1.
Yep. So if 1 is a root, x minus 1 is a factor. And now the last one is 3 is a root. So what would be the factor there?
X minus 3.
X minus 3. Now, it's just a matter of multiplying that out. So when you FOIL it, you're going to get x squared minus x plus 2x, and then 2 times -1. Well, that's what you get when you do the first 2. So we're working backwards from the roots to figure out what the original problem must have been. Now we've got to FOIL one more time. So x cubed, x squared, minus 2x, minus 3x squared minus 3x plus 6. So this must have been the original problem to get those as roots. X cubed plus x squared minus 3x squared is going to give me
-2x squared.
2x squared. Yep. And negative 2x and negative 3x gives me, yep, good. And the only thing I have left is my constant, and there's nothing to combine it with. And nice thing about this is you can type that in on a calculator, check it, and it should cross the x-axis exactly at -2, +1, +3. It's a lot easier to be given the roots and then figure out where they came from than to start with something and then try to factor it. Again, I'm not sure this is something people would know how to factor at this point unless I gave you one of these factors to start with. Then you could divide and get the other ones. But I would probably have to give you one of them to start with at this point. Yeah.
Is that something we would be taught?
Not today.
Well, not today, but like at some point.
Yes. Yep.
Yep, it worked.
Yep, it'll work. The only mistake you could make is really foiling these out, but just be careful with it. You'll generally never have more than 3 of them. I mean, if you had 4 or 5 of them, you just got to keep doing it. But then it starts to take a little while to do. Okay, so, well, actually this kind of ties in with your question. Are we going to learn how to factor something like this? No. Like this? Yes. This isn't quite the same factoring. This is a little easier to factor. Factor by grouping is when you factor what you can out of the first 2 and then what you can out of the second 2. Factor by grouping wouldn't work on this problem. What's that?
Why?
Because the last 2 have nothing in common to factor out. If this was like a 9 and a 6, then you could like take a 3 out of both. But there's nothing to factor out of -5x plus 6. There is here. You could factor out an x squared. But the method I'm about to show you would not work on this problem. It will work on this one. Even though it looks the same. Something cubed, something squared, constant. These numbers are nicer. What can you factor out of the first 2 terms? Yep.
X squared?
Okay. And what does that leave you with if you pull an x squared out from each term here?
X plus 2.
Yep. Now the goal with factor by grouping is to end up with x plus 2. Again, if you do, you can do factor by grouping. If you don't, you can't. So now look at these last 2. -4x minus 8. What can you factor out of those? Yeah?
You can factor out a -2 out of them both.
You can. Can you do even more?
Negative.
You
Yep.
could do negative.
You do -4. And what does that leave you with if you factor a -4 out?
X and 2.
X and 2. So we factored what we could out of here, then out of there separate.
Does it just happen to be the same?
It has to be the same with factor by grouping. That's how it works. It has to come out the same. If it doesn't, you can't do factor by grouping. In the last problem, you could. So now, we're going to look at that, and look at that, and factor out what those have in common. In the green section, what do both of them have in common?
X plus 2.
So pull that out. If you take that out of the first one, what's all you have left?
X squared minus 4.
And then when you take it out of the second one, what do you have left?
X squared minus 4.
Minus 4. Now, what you have here is kind of like what we had at this step. Something squared, and then something to the first power. So we got to take it back one more step to get it to 3 separate factors. So we have to look at this one. X squared minus 4, that's a difference of 2 squares. How does x squared minus 4 factor?
Now x plus 2 and x minus 2.
Perfect. Now you've got your 3 individual factors, and you're basically at this step. Now you just have to work backwards to get the numbers from those 3 factors.
We can only get 2 out of them.
That's okay.
It's like two of the same.
We have x plus 2 squared, and then
Right. So what would you plug in for x here?
that would be -2.
-2. And here?
-2.
You don't have to write -2 twice. There's a name for that. It's called a repeated root. You don't have to write it twice.
Would you like, you can put that up to the graph, would you not even see anything?
What's going to happen at a repeated root is it comes up, it touches the axis at that number, and then it bounces away from it because it can only cross the x-axis in 2 spots. If it crossed in all 3, it would do this. 3 different numbers. But that's what this one's going to look like. Something like that. So it crosses at -2 and where else? +2. So again, would this method work on the last problem? No. But it will work if you have really nice numbers.
So no matter what, the absolute value of x needs to equal 2.
Yeah, in this problem you could write it that way. It's not always symmetrical. Like if you get -5 as an answer, you're not always going to get +5. Doesn't always work that way. Okay, so these are the questions. Actually, I can simplify that because I took one of them out. It's 9 through 21 odd.